Hey everyone, we've brought ourselves right up to the crux where we're talking about being able to send unicast communications between devices, how duplex and speed impact things, and I mentioned the fact that in the confines of working as CCNAs, we need to be aware of what can go wrong. And that's going to be the golden rule in networking. Nothing is going to last forever. Things are going to break. And what I want to do is I want to discuss what happens when they break and how we can actually deal with some of the most common switch media related troubleshooting issues that we can possibly run into. Now, we need to recognize out of the gate, we have some go-to tools that we can use. Among them, the most useful is going to be the idea of being able to ping. Ping is a utility that allows me to be able to ping from one logical address to another. And I can even employ the concept of DNS, one of the services that we're going to end up talking about, domain name services, that's going to allow me to be able to make certain even that's working. So rather than pinging an address, an IP address, I could ping a URL style address. And it would ultimately resolve it to the IP address that's being used in the infrastructure. Now what we're going to see here is we're going to want to have exclamation points come back. Now, when we do this, when we actually have the implementation, we do the ping, sometimes we may see dot, dot, exclamation point, exclamation, exclamation point. What we need to recognize is Cisco devices, by default, are going to send 5 ping messages. Those are referred to as ICMP messages, and we're going to expect to see 5 ICMP echo replies. So we're going to send ICMP echoes out, and we're going to expect a reply to come back, one for each ping that we send out. The exclamation points mean we received the echo reply to our echo. The dot means we did not receive it. Now what we have to be prepared for here is sometimes, remember we talked about that process of that MAC table implementation. Sometimes we have to be careful or at least mindful of the fact that our first set of pings aren't going to work because we have to go through that ARP process where we're going to take the IP address and learn the MAC address for that as a destination, and in order to send information back, whereby we have our bidirectional communication method. And sometimes it takes a little while for that to get pinged up now, or pinned up. Now what we recognize here, this is about a 2-second window. So between these there's about 2 seconds difference. So it may take either 2 seconds, sometimes 4 seconds. Depending on the media type, I've seen it take maybe 3. So sometimes it'll be dot, 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 exclamation, exclamation. Now if we ping again, it'll be 5 exclamation points, because remember, all the information that exists in that MAC address table now has been populated. So we don't have to go through that process. So recognize the fact that ping can be used as probably one of the handiest troubleshooting tools that we have available to us as network engineers. Another way that we can access to test things is to verify reachability to given components, and we also are going to want to be able to contact or connect to that CLI that I was talking about, the command line interface. Remember, in the confines of Cisco, CLI is king, and I'm hoping that that will never ever change. Now in order to be able to get to that, we have to recognize that I could access it from a router by typing the telnet command. I can access it from something called a terminal server, or I can actually connect directly to an IP assigned to a device. Remember, I said we have the management VLAN, sometimes referred to as VLAN 1, interface VLAN, the SVI concept, or any physical IP address that's been assigned to a given device, a switch, a router. We can use that for the purposes of managing, and we can do it by telnetting if telnet has been configured and enabled so that we can access our system. Now in the confines of being able to do that, there's going to be some tools. There are things like the hyperterminal in Windows back in the day. You can actually use the command line now if you can go in and just get into a Windows DOS shell. You can also use tools like, example here to my immediate distant here is going to be using a software tool called PuTTY, which is free. And we'll, again, when it comes to actually accessing live gear, we'll be looking at each of these as options. But bear in mind that in order to access CLI, we need an emulator to be able to use telnet communication. We have other options. We can use SSH and things along those lines, but telnet is unsecure. Secure shell SSH is going to allow us to be able to connect to our devices. Now, once we're connected, we need to be aware of what type of problems it is that we're going to be looking for or working with. Now, when we start looking at it, they're going to be broken into a number of categories. The first category that I'm going to talk about are referred to as media-related issues. Now, media-related issues are going to come to us initially in the form of copper. So when we start looking at this, like I said, remember, these copper cables act like antennas. And antennas can transmit signals and they can also receive signals. Now what we want to do is we want to mitigate that process, and one of the ways that we talked about it in the confines of UTP was to use the rotations, the twists, the actual unshielded twisted pairs. Take the pairs and rotate them together. That's going to allow any of the signals that they may radiate to clash with each other so they're not going to go out and they're going to be actually attenuated. And it's also going to stop us from picking up signals from other connections in the form of crosstalk, or what more accurately is referred to as stray impedance. So that's when the wires are acting like an antenna receiving signals. We can pick up signals from almost any RFI source. RFI, radio frequency interference, but there's also another value that we need to take into account, because it's not just RFI that we have to be concerned with. There's also EMI. RFI stands for radio frequency interference. EMI stands for electromagnetic interference. Now that's important because a fan motor has magnets in it. It's an actual generator that's just being used to move the fan. It's a motor. Well, when we have stray lines of magnetic flux that are crossing each other, what ends up happening is it begins to radiate electromagnetic interference. Our copper cables are we use copper for one of the primary reasons is the fact that copper allows me to conduct signals very, very well, very, very easily, and over large distances or medium distances. Well, the problem is that that same rule means that we're also going to be very susceptible to something called EMI, electromagnetic interference, which can cause us a lot of problems in the confines of our Ethernet infrastructure in certain environments, machine environments, the manufacturing floor of a particular plant, the X-ray areas, or some of the equipment areas in hospitals. Now, other solutions include the fact that, sometimes wires get damaged. So a cabling can get damaged, whether it's like this. This is a coax. It looks cool. It's a coaxial connection. All right. But whether it's coaxial or UTP, it happens all the time. One of the most common things I've seen happen is people in office environments, they move their machines around, and the next thing you know, they're taking their chairs with those little rollers, and what they're doing is they're rolling over top of their cable, Cat5 cable, back and forth, back and forth, back and forth. I mean, I saw a guy almost cut one in half. But, I mean, you got to take into account, you got a concrete slab, you got a little itty-bitty thin mat of carpet in most of these office buildings, and yet they've got those plastic wheeled chairs, and they're just devastating their cable as they go back and forth across it. I've also seen scenarios where the cable runs have been ground against, say for instance, the bands or brackets that come down holding the ductwork. Again, all normally part and parcel of poor cable installation, but it does happen. And sometimes things get damaged while you're installing new cables. One of my favorite ones, and I run into it time and time again, is that you're constantly replacing equipment, and if you take a look on the end of the RJ45 connection, there's this little plastic clip that when you plug it in, it snaps and it holds the cable in so the cable doesn't come out. I cannot tell you how many times I've gone to client sites and I found that stinking little itty-bitty plastic tab popped off, broken, and they just stick the cable back in there and they don't worry about it. Well, 3 months down the road, somebody replaces a switch and bumps into it or pulls it a little bit and it comes out just enough to break the connection. And next thing you know, we've got either a dead unit or a dead end, or we've lost a port-to-port channel, or we've lost an individual link going to a switch. All can be mind-numbingly painful when it comes to working with this style of connectivity. Now, another part of this is that we have to recognize, like I said, fiber. And we have this idea of a macro bend. Now, macro bends are good. It's micro bends that are a problem. And when I was talking about the idea of bending our fiber, I said if we bend it greater than 90 degrees, I meant 90 degrees from the straight line. So this is a 90-degree angle. So if the bend was less than 90 degrees, or an acute angle, what ends up happening is that's where we begin seeing problems. However, it's a little bit more specific than that. What I want you guys to understand is that there's different ways of looking at how things are implemented. So what I meant was I have my straight line. So if I were to bend this cable this way, greater than 90 degrees, then I can have a problem. Now, even if I bend it 90 degrees, and I need to understand what this idea here is of a radius. So when I look at radius, that means I have a circle. So if my 90-degree bend takes place over a surface or over a circumference, well, actually this would be a diameter, of greater than or less than 25 to 30 millimeters, then what's going to happen is that the idea is that light could actually escape the cladding. So as long as my radius is greater than 25 to 30, so actually I said diameter, so this would be radius. So as long as from the center to the furthest point was no greater or less, is not less than 25 to 30 millimeters, what ends up happening is I'm good to go. But the problem is like I said, when we take that copper, when we take that core and we bend it, what we have to recognize here is that we have the cladding around it. Now, the main thing that I want you to understand is that as we bend, what ends up happening is that we're actually causing the center conductor, the glass, to actually physically kind of push through the cladding. So by virtue of that, what ends up happening is light leaks out of this bend. We can have a 100% loss where all the light leaks out, or we can have marginal loss where only a small amount of the light leaks out. But the direct effect here is that the more light we lose, the less distance we can travel. And the whole reason that we have fiber optics in the first place is so that we can shoot our Ethernet communications across greater distance than those supported by copper. Now, the other idea here is that when we start running into this, it's important to understand that we have a number of ways that we can actually troubleshoot. Now, when we look at this, what we're going to do is let's just follow this flow chart and then we'll move on. That'll give you guys plenty of time to be able to copy it because it's definitely worth looking at. But what I want to do first, before we even follow this, is I want to look at the three modes, the three interfaces. Notice that we're using the same command. So show interface, show interface, show interface. And what that's going to do is it's going to allow us to verify the status of the interface. That same command allows us to check for excessive noise, and that same command allows us to check for collisions. Now, Terry, I thought you told me that collisions were absorbed by switches. They are. However, what we also have to recognize is that nothing works forever. So there can be situations whereby we may have a bad port, we could have a bad SFP. Actually, I found an SFP. Let me bring myself up here. This is a small form factor pluggable module. It's for a gigabit Ethernet connection, so it's copper. So what ends up happening is you take this component and you plug it into your switch such that it's only going to have about that much sticking out, and then you plug your cables into it. Now, depending on what small form factor pluggable module you have is going to determine what type of media you can support. They come in fiber optic, they come in copper. So the main idea is I just want to give you guys an example of what one looks like. I mean, it's much ado about nothing when you look at its overall size, but it is definitely something that we need to look at. And since it's replaceable because they have a tendency to go bad. So it's easier to replace one of these than it is to try to replace an entire switch. Now, keeping in mind that when one of these goes bad or when a port goes bad, we can run into situations where we can have collisions. Why would we have collisions? Well, we would have collisions when we cannot negotiate. There's no full duplex. Now, we talked about us setting this up and configuring these devices and saying, well, if I go auto and I go half, I'm only going to negotiate half. Well, the problem is that I may be auto on both ends, but something could happen to the SFP or something could happen to the port that's going to cause the system to lose the ability to negotiate. And I could step down to half duplex, still sending signals back and forth, but now I have the capability of seeing collisions. So we're going to look at exactly what's involved in that process. So when we look at this, what we need to recognize is, first of all, we have no or we have a bad connection. So So we got one, we have nothing, or we have a crappy connection. Well, the first thing that they're going to say is verify the interface status. If the status is operational, then we're going to move on in the troubleshooting process. If the status is down, we need to fix what's down. 9 times out of 10, this is going to be caused by bad connectors or bad cables. So you got that moron with the chair rolling over his cable, or you've got that guy who's in a really, really big hurry to go home because he wants to watch the football game, and he didn't change the category 5 cable that's got the broken clip on it. That's the kind of stuff that will get you invariably when you least expect it. Well, if that's okay, if everything's operational, what we want to do is we want to check for excessive noise. Well, Terry, what do you mean by noise? Well, guys, RFI, radio frequency interference, and electromagnetic interference manifests on our lines and on our cables in the form of noise. And we can see that using the show interface command. So again, very, very handy tool for us to be able to work with. Lastly, we may have this idea of excessive collisions, which means we're not able to negotiate full duplex throughput. So in other words, the way we need to do that is we need to, again, use the show interface command. We'll see the collisions, and then we need to verify and fix any possible duplex configurations that we have. And if we've addressed all of those scenarios, bam, Cisco says it's fixed. And I really and truly haven't seen a scenario in a real-world environment where one of these 3 things wasn't causing this particular type of problem when it was associated to switching media issues. Now, switching media issues are not always, or not the only problems or issues that we can run into. But we do need to continue to explore them. So the key thing here was, as we said, we can do the show interface. Now, the first thing I want to verify was that idea that we illustrated, and that is going to be, is the line up? So notice right here, I have fast Ethernet 01 is up and up. That's the line is up and the line protocol is up. Now when we look at this, these mean specific things. Up and up means that everything is 100% good to go, we're operational, and this is going to be the norm that we're going to want to implement. Sometimes we'll see a scenario where we're up and we're down. Now what does that mean? Anytime you see up, down, you have a connection problem. So go in there and troubleshoot that connection problem and mitigate it. Now the other thing that we're going to find here is down, down, not connected. I mean, that's kind of a no-brainer. Not connected tells me my cable's unplugged. One end of the link is going to be unplugged or set up. Now less easier to troubleshoot is down, down. Now more often, when I have down, down, I'm going to have some type of interface problem that I need to troubleshoot. And that's going to be, again, indicated in this scenario here where it's going to say down, down. Now, the other command that you're going to run into, and this is the one that I call the self-perpetuating troubleshooting opportunity, and that's going to be what we see behind me, which is going to be administratively down. That's when you've shut the interface down. And it's going to say administratively down, down, which means I have gone so far as to disable the connection. I've gone in and typed shut under the command. So looking at this, these are going to be almost all of the scenarios that we're going to run into when it comes to working with these individual interfaces with regard to that up-up scenario. Now, when we come and we look at this notion, what else gets continued? So we've looked at verify interface status. The next option was that what we wanted to do is we can look at this idea of excessive noise. Let me grab my pen here. Excessive noise, what we're going to do is this is going to be CRC errors. CRC stands for cyclic redundancy checks. Anytime we start seeing lots of CRC errors on our links, we know we have some kind of excessive noise scenario. Now what does that mean? That means you need to start looking for things like fluorescent light ballasts. 9 times out of 10, somebody took a shortcut and they run the cable directly over top of the can that holds the fluorescent lights. Inside of that assembly is what's referred to as a ballast. It's a step-down transformer allowed to actually it's not even it's a step-down current, step-down voltage, but it ups the current. And the moment that starts happening, it becomes a radio frequency emitter. And actually EMI emitter also. So the thing here is look for that kind of thing. I had a scenario, I had a client that would, it wasn't consistent. We couldn't find out what the problem was. There would be odd days. 9 times out of 10, it centered around lunchtime. We could not figure out what was causing the EMI. We kept getting cyclic redundancy checks, and it was 9 times out of 10 around lunch, but sometimes it would be late in the evenings, and then they'd call us in and we'd get to troubleshoot, because what happened was we had really bad signal. We had no throughput. Sometimes it would go down. And what we ended up finding out that it was in the lunchroom, they had a microwave. And the microwave had a cracked casing on it. And directly behind the microwave was the closet that had the primary vertical cable runs that were going between the closets. And when they would hit the microwave to start heating up their food during the lunch break, the EMI would basically cause problems associated with the lines. So we ended up replacing a microwave to fix a network problem. But again, definitely something that we want to make certain that we're aware of exists as a possibility. EMI can be possibly one of the hardest things to troubleshoot, but fortunately, we have this idea of the CRC errors that's going to tell us how to find it. And again, what we want to do is we want to check cables for damage. We want to make certain that the cables are the right length. If the cables are too long for copper or whatever, then we need to make certain that we either put another switch in or some type of repeater to recondition the signal. And also, we're going to have to start looking for noise sources, typically RFI or EMI generators. Now, the other idea was excessive collisions. So excessive collisions, 9 times out of 10, are going to happen because we drop our switch out of full duplex. So half duplex can obviously be a direct responsibility for these, or a cause for these. Now, what we also want to recognize here is that when we have the excessive collisions, let me go ahead and erase some of this. Excessive collisions, 90% of the time, let's say 99% of the time, are going to be caused by a half duplex operation. So when we want to do that, we want to make certain that we configure that link to use full duplex. Now, we also have another condition here that's referred to as excessive late collisions. Now, an excessive late collision means that we have some type of duplex mismatch. Now, this could be either caused by having we've gone in and we've done full and we've done auto, or I'm sorry, we've done full and we've done half. It could be configured where we have full and we have auto, and something has happened to the device that has disabled the ability for it to do auto, so it's going to fall back to half. So that means we're going to have this scenario, which is why Cisco recommends that on our infrastructure links, we go ahead and manually configure this and do not rely on things like auto negotiation to get signals through. Now, looking at exactly what's involved from this point on, what we have to do is we have to understand, again, the significance of these commands. Now, when we look at it, what we can see here is, for instance, in this output, we're, again, looking at the show command for show interface, fast Ethernet, and we're picking on fast Ethernet 01. Notice we're up and we're up. But that doesn't necessarily mean that everything's good. We need to look at more information to determine whether or not everything is operational. Notice right here, we have CRC errors. In fact, we have 3 CRC errors. Now, I would expect to see 0 of these. So anything more than 0, I'd definitely be concerned about. So this tells me I've probably got RFI or EMI issues in my infrastructure. Also notice in this scenario, we're completely ate up, because out of 1,932 output, I have 1,790 errors as a direct result of collisions. So this is going to tell me right now that I've also probably got a duplex issue in this scenario. But add to that, I've also got 131 late collisions. So I've probably got a duplex mismatch somewhere. And it's always going to be associated with this link. So as you can see, this one show command offers us a huge amount of turnaround and a huge amount of benefit with regard to being able to understand exactly what's happening on this link. Now, bear in mind, we're not going to have duplex operation unless we have the capability of having point-to-point connectivity. So bear in mind, it's going to be through the protection or the configuration of our system by hardwiring it that we're actually going to mitigate some of these risks. But what I want to do is I want to take a look at some additional port issues that we're going to have. Well, when we look at it, 90% of our problems that are associated with duplex problems are going to be a direct result of some type of mismatch in the duplex setting. It can be a manual duplex issue where we have full on one side and auto, which should negotiate full. But what we have to recognize here is that sometimes this device may lose its ability to auto-negotiate, and what it would do is it would default back to half, which means now I have a mismatch. Which means I may be sending some data, I may be sending no data. The other thing here is that we need to realize here that it also can be related to duplex and speed issues. So in this scenario, if I have 100 as my speed and I'm using auto here, my link pulses are going to travel across this link. They're going to negotiate the speed, and it should match to 100 and everything should be good to go. Check, check. But the problem is what happens if this switch loses its ability to negotiate, either through the instance of a bad cable or the possibility of a bad port. Well, what will end up happening is we have the capability of having 100 on this side and 10 on this side. Or it could be 100 on this side and it could be 1 gig on this side. And it's going to be that type of mismatch that can cause us lots of problems when it comes to trying to ensure that our ports are going to be up and operational. Now, also keep in mind, there are rules, governances that we need to really pay attention to, and we can look at some of these by way of citing some examples. So when we look at this, and we have the idea of we can have full duplex, one end is set to full duplex, the other end is set to half duplex. That's going to result in a mismatch. So that's one problem. That's going to typically be an admin issue. We went in and we messed everything up. We can also have the scenario, like I said, where one end is set to full duplex and the other end is set to auto-negotiate. Well, that should work. It should negotiate full, and everything should be up and operational, and we should have optimum throughput. But like I said, what happens when auto-negotiation fails on one end? Well, that means that more often than not, the one end that failed is going to revert to half duplex. That's going to result in a mismatch. Now, we also have the idea where we have half duplex and the other side is set to auto-negotiation. So if auto-negotiation fails in that instance, that end is going to revert to half duplex. And what we're going to find here is that we're going to have both ends at half duplex, which means there's not going to be a mismatch. So we're going to have throughput, but what we're going to find here is that it's going to work the way we wanted it to. Because if I had auto-negotiation configured on one side and half duplex on the other, I want it in half. So we just have to be aware of the different scenarios and the different situations that can actually occur when we're setting these systems up. And 9 times out of 10, it's not something that we did out of the gate that was wrong. It was something that actually happens as a direct result of some type of failure, which is going to extend to us a troubleshooting opportunity. Now, we also have some other issues that I want to make certain that we highlight. So notice here, it's like we need some more examples of duplex-related problems. So one end fails to do full duplex. The other end fails to do half duplex. Well, what will end up happening? Here's an example. So I have a gigabit Ethernet interface that's going to default to full duplex here. And I have a 10100 that's going to default to half duplex here. We've got auto set up on both ends. So this one will want to negotiate full, this one will want to negotiate half. We're going to use an auto configuration tool to enable or to see if that happens. Well, what happens here is if the auto negotiation fails on both ends, they're both going to revert to half duplex. Both ends are going to be set to half duplex, therefore there's not going to be a mismatch. So it's not necessarily just understanding the hard and fast rules as much as it is understanding the fact that it's going to be based on the default behavior of our given interfaces. So if we say we want to go auto on both sides, we just need to make certain that we understand that there are going to be circumstances and situations where things can fall apart, which is one of the reasons, like I've said time and time again, up to this point, that Cisco recommends that we do our full negotiation, we set up our links and our infrastructure to support doing things statically. We don't want to use auto-negotiate. Now, in another scenario, so let's embrace the idea of a speed problem. So in here, what we're going to do is we're going to have a speed. Notice I'm 10 on this side and 100 on this side. I'm auto on this side. So ideally, in the best case scenario, this should negotiate a 100 link based on the auto capability here. Now, when we look at this, what we're going to find here is that one end's set for one speed, the other is set for another. Now, what that's going to do is that's going to result in a mismatch. The end one end is set to a higher speed and not a negotiation, that's the scenario that we have down here, is enabled on the other end. What happens if auto negotiation fails on this switch? The switch senses what the other end is using, and it's going to revert to the optimal speed to communicate. So if this is a 10, 100, 1000, what's going to happen is it's going to see 100 and it's going to go to that particular mode. Now what happens if I have auto set on both sides? Well, if auto is set on both sides, what happens here is the auto, it's going to negotiate the best speed, but let's say, again, we've lost the ability over here on this switch. Auto negotiations failed. This time it's failed on both ends. So it's down here, down there. Well, what they're going to do is they're going to revert to their lowest speed. That means both end speeds are going to be matching because the speed is going to be 10 megabits, and therefore there's going to be no mismatch. Now, what I've described here is a number of scenarios that Cisco's put into place that have represented the fact that we want to make certain that in the event of a failure, whether it's on an individual end or if it's on both ends of the link, what's going to happen is we're still going to have throughput. It may not be optimal, but we're going to have throughput with regard to being able to send information. Again, we want to make certain that we've protected our infrastructure links. Again, hardwire them where necessary. But the whole thing is that, keep in mind, auto is very, very handy for desktop configurations because tomorrow your user may have 100 megabit. Today, they may get another computer that's going to be operating at 1 gig. So long as we have the capability of being able to negotiate to the optimum speed of the network card installed on this computer, then what we're going to do is we're going to want to use auto with regard to speed connections and duplex connections facing our users. But on our infrastructure links, definitely take the opportunity to do the hardwire and bring it up and make sure it's operational. That concludes this portion of our lesson. I'll see you guys in the next video. Bye-bye.